I want to talk also, so composites, one, just one of the structural engineering kind of 101 in college, you do kind of your mock-ups of composites, and you come up with some of these conclusions of, wow, look at how much stronger for a given density or for a given weight this can be. And I think we were using fiberglass or something at the time. That went along. So I think I mentioned offline, one of my first job out of college was at Boeing and interiors and working on interior components, especially on the 787 Dreamliner that I was working on. I mean, everything's composite, whether it's fiberglass or carbon fiber or a mix of the two. But one of the challenges and the drawbacks, so we were using pre-preg, kind of a carbon fiber sheet, right? Which then you have to bake, and you can cut the shape and things. And one of the challenges there, so it's super light, relatively strong, but it's uniform, right? So you can't be particularly intelligent about where you're putting the strength, where you're reinforcing things. And I think some of the examples that you gave, whether it's a steering column or certain automotive applications, you don't necessarily need uniform strength, right? Coming into something exactly where you're going to have the spots that need to be more reinforced, and where maybe you can pull out some material and try to cut weight. But that's easier said than done. Can you speak to how you think about this?
That's exactly the point. So and this is, to my understanding, is exactly the point why we have certain disappointment, actually, especially in aerospace. There is a bit of disappointment in the industry in composite materials. There's been a lot of enthusiasm when all these programs like composite jet plane programs were started like a couple of decades ago. But now there is a disappointment. And the problem is that composites are there for several decades, but the design approach, the way they are designed and made, is what we call metal thinking, or we handle, or we design and we manufacture and we treat and we post-process composites the same way as we did it before with metals. And it all comes from design, and it all comes from design complexity. And composites are much more complex by nature, and so the design approaches are much more complex. But in order to use them, in order to start using composites, because there was no, theory, there was not so much theory behind how to simulate or estimate the behavior of the composites. So the same simple methods, more or less the same simple methods, were applied to composites as they were for metals. And then again, with the manufacturing, when because that's what we call black aluminum, because composites, especially like fiber-reinforced composites, they are anisotropic by nature, so they are directional by nature. And this is the biggest difference of composites compared to metals, because you have fibers which are directional, and composites are isotropic, so they are omnidirectional, so they have the same properties in every direction. And but all the design methods, they were for isotropic materials. So people decided, okay, so we would just make what they call a quasi-isotropic material out of composite material, and then we can work with that as if it was isotropic or as if it was metal. So they start putting these layers or fabrics in a certain second sequence, which they call laminate. And this package, they were putting the fibers in multiple directions, so that overall it's like omnidirectional or quasi-isotropic, as they call it. And then they thought, or they still think, that you can then apply the same design approach as more or less as it was for metal. But basically this is kills all the advantages of composites. So a very simple example, again, if we're getting back to this relative strength and stiffness. So if you take aluminum, then aluminum on average has the strength of 400 megapascal and the density of like 2.7 grams per cubic meter. Now, remember that. And then carbon fiber reinforced composite has the strength of over 2 gigapascal, so more than 5 times more compared to aluminum, and its density is 1.7, so about a half, a bit more than half of aluminum. So it would mean that you can make structures that are up to 10 times lighter compared to aluminum. But that's for unidirection. Now, when you make a QI, a quasi-isotropic laminate, now you have isotropic strength, but it's only 300. So it's less than aluminum. And so it becomes less strong than aluminum. And the density is less, but instead of having like 10 times, it's like 20, 30% more now, the relative strength.